Welcome all of you to tutorial number 6. In this tutorial, we will be taking a couple of numerical questions associated with the basic design principles in cache memory. Over the lecture videos that was released in this week, you might have seen the basics of the cache memory and what do you mean by cache memory mapping and different cache block replacement techniques. This tutorial is designed keeping those topics that we have discussed in this week to get more clarity on the concepts that you have already viewed in the lecture videos. Our first question is on, for a 32 KB direct mapped cache with 64 byte cache block, give the address of the starting byte of the first word in the block that contains the address 0x7245E824. So, here we have a direct mapped cache where we have multiple blocks inside the cache. Now, when you bring from main memory, you are actually transferring a block of data. Let us say this is the block of data that gets transferred into this particular block. Now, if this cache is a 32 KB direct mapped cache and the block size, this block size is 64 bytes, give the address of the starting byte of the first word in the block that contains the address 0x7245E824. So, what the question is, let us say the address 0x7245E824 that is located, let us say, midway inside a cache block. The question that is asked is, what will be the address of the starting byte of the first word in the block that contains this particular address. We have to understand that when you bring contents from the main memory, you are bringing a block of data and these are continuous blocks inside the main memory. So, if you look at the address of those words that are brought into one cache block, they will differ only in the few least significant bits, whereas the most significant bits of the address will be same. So, when you move to the very adjacent byte inside main memory, only there is a change in the LSBs. So, keeping this in mind, let us try to understand what is the context given in this question. So, it is a 32 KB direct mapped cache with 64 byte cache block. So, let us first find out how many sets are there in the cache. So, this is a direct mapped cache. So, the number of sets will be equal to the number of cache lines or cache block. Number of sets is defined as cache size divided by block size into associativity. So, here the cache is 32 KB. So, when you have 32 KB, we will try to represent them in power of 2. 32 is 2 power 5 and kilo is 2 power 10. So, that means we have total of 2 power 15 bytes that is there in this particular cache. So, 2 power 15 which represents 32 KB divided by, in the denominator we have block size. We know that the block size is 64 bytes, 64 is 2 power 6 and the associativity is 1 because it is a direct mapped cache. So, it is 2 power 15 divided by 2 power 6, it is 2 power 9. So, this particular cache has 512 sets inside it. Now, we have to divide the physical address into tag, index and offset, but we do not know what is the total physical addressability, the number of bits in the physical address. Anyway, let us imagine that we have an n bit physical address, out of which the middle few bits is for set index. Since we have 512 sets which is equal to 2 power 9 what is been showed, 9 bits in the physical address is used for indexing and the block size is 64 bytes. So, the last 6 bits is used for offset and the remaining bit is for the tag. Anyway, here the tag bit is not relevant. So, what is the meaning of this? The last 6 bits of the address will represent the offset. That means, if I have some address A and another address B, if they belong to the same block, then they differ only at most in the last 6 bits, whereas all other more significant bits will be same. So, let us write the address that is being asked. 0x7245E824, it is written in hexadecimal. This is a 32-bit address where each of these represents a 4-bit value. Let us take the last 2 digits in the hexadecimal notation 2, 4. If I expand into hexadecimal, 2 can be written as 0010 and 4 is written as 0100. Now, out of this last 8 bits which comes in the address, the last 6 bit will represent offset. So, what you see in this blue color, that is the offset portion. So, this is the offset that is been given. Now, the block address typically range from whatever is the most significant bits, it is not going to change. The last 6 bits will range from 6 zeros all the way up to 6 ones, whereas the remaining most significant bits will remain same. So, if you put all zeros for this particular address that is been given, if the last 6 bit of the address that is been given in the question, if I make it 0, then it becomes 7245E800, that is the address of the first byte in the block, and 7245E83F, that is the address of the last byte in the block. So, the starting address is then this one, 7245E800. So, what we have done in this question? In this question, a cache memory detail is being given, the block size is being mentioned. All what we have to understand is, when we copy something from main memory into the cache, continuous bytes are being copied. So, if you examine the address of these bytes that belong to one cache block, they differ only in the least significant bits. How many least significant bit? It is been defined by the offset bits. What is the block size? In this particular question, the block size is 64 bytes. That means the bytes that are part of one block will differ only in the last 6 bits of its address. So, if the last 6 bit, if you completely put 0, that is the very first byte, and then all combinations of those 6 bit will give you different byte in the same block, ending with the last 6 bit values given to all ones. Let us now move on to the second question. It is basically on index and offset calculation. A cache has 512 KB capacity, 4 byte word, 64 byte block, and it is 8-way associative. The system is using 32-bit address. Given the following addresses, which set of the cache will be searched, and specify which word of the selected cache block will be forwarded if it is a hit in the cache. Let me try to restate this question. Given an address and given a specification of a cache, now in this context, we want to know, to understand where in cache memory the address matching happens. We are not searching in the entire cache. We know that cache is a very fast memory. It is going to respond back to the processor request quickly because it localizes its search to limited location. Now, this particular question where I am giving an address, and the question is, where in the cache, in which set of the cache tag matching happens, and if it is a hit, then there is a big block wherein we get a hit. Inside the block, which is the word that gets transferred. So, first we have to understand the split up of the physical address. Any given cache memory question with specification like this, we have to find out the split up of the address from tag, index and offset, and it is the index bit that will tell you which set the search is. And once you know the index number, and then in that particular set index, the tag matching has to happen, and if at all there is a match, then the offset will tell you which word is to be transferred. It will be more clear to you once we understand this example in its detailed working. So, this is the details that has been given. It is a 512 KB cache with 4 byte word and 64 byte block. It is a 4 byte word. So, if it have 64 byte blocks, and if you divide it into 4 bytes, then there are 16 words that get stored in one block. It is 8-way associative. So, the first one is number of sets is equal to, same like the previous question, cache size divided by block size into associativity. Here cache size is 512 KB, 512 is 2 power 9 and Ka is 2 power 10. So, 2 power 19, that is your 512 KB. Block size is 64 bytes, so it is 2 power 6. And associativity, it is 8, it is an 8-way associative cache, so it is 2 power 3. So, we will get 2 power sets. This particular cache has 1024 sets in it. It is mentioned that one word equal to 4 bytes. Hence, 64 byte block can accommodate 64 byte divided by 4 byte 16 words. That is been shown in our previous calculation. So, if you have 1024 sets, then there are 10 bits that is gone for index. We have total of 32-bit address that has been given in the question. So, this 32-bit address, inside that 10 bit is going for index, and these 10 bits will tell you which is a set out of 1024 set, which set has to be searched. And then we have an offset that is equal to 6 bits for the offset, because it is 64 byte cache block. Now, out of the 6 bit, the first 4 bit will tell you the word number. The next 2 bit will tell you which is the byte within this word. We have to understand, here we have 4 bytes, and it is 4 continuous bytes that form one word. So, the address of the bytes within a word, they will differ only in the last 2 bits. That is why in the offset that is being given, out of the 6 bit in the offset, the first 4 bit is for the word number and the next 2 bit is for the offset. So, let us now consider the address 0xabc89984. So, we have seen that out of the 32-bit address, the physical address is 32-bit, most significant 16-bit is tag, next 10-bit is index, and the last 6-bit is the offset. So, in this address, whatever is given in the red portion, they constitute the last 16 bits. I am expanding the last 16 bits. 9 stands for 1001, again 9 1001, 8 is 1000, and 4 is 0100. And here the blue portion, that is a 10-bit blue portion, indicates a set number. The 4-bit red portion indicate the word number, and the 2-bit green is telling the byte within the word. So, if you compute the decimal value of this blue portion, this 10-bit blue, you will get a number 614. If all the values of blue bits are equal to 1, then that corresponds to 1023, set number 1023. So, in this particular address, these 10 bits constitute a decimal value 614, and if you look at the red portion, it is word number 1. That means, when you get this particular address ABC89984 into a cache memory, the set 614 is being searched. In set 614, since it is 8-way associative, there are 8 cache lines. In all the 8 cache lines, we see whether the tag value stored is same as this 16-bit ABC8, that hexadecimal ABC8 is the tag that is saved. If the tag is matching, then in that particular block where the match was there, you transfer the very first, you transfer word number 1, not word number 0. The very first one is word number 0, this is word number 1. So, transfer word number 1, that is the required one. Similar to that, if you explore the second address 485669AC, the red portion indicates the last 16 bit, expanding that 6 is 0110, 9 is 1001, A is 1010, and C is 1100. So, the blue portion indicates set number 422, and the red portion indicates word number, it is word 11. So, the search is restricted only to set number 422. Within that, perform a tag comparison, and whichever block get a cache hit on the tag match, then in that particular block transfer word number 11. So, to summarize what we do in this question, whenever you get the cache details and the address, find out the set index portion, and that will tell you which is a set is to be searched, and then you find out the corresponding offset. So, from the binary value, find out the decimal, and that is the set wherein the search for tag match happens. Now, the next problem is on tag and data array access. It takes 3 nanoseconds to access the tag array value and 4.2 nanosecond to access the data array value. 1.3 nanosecond is taken to perform hit or miss comparison, and 1 nanosecond to return the selected data to the processor. So, we have to understand that there is a tag array portion and there is a data array portion, and time to access tag and data array portions are different. And after the tag is being accessed, you perform a hit or miss comparison. So, that happens after the tag array operation, and once the hit happens, then it takes some time. Here in this case, it is 1 nanosecond time to return the selected data. What is the cache hit latency of the system? And then The second portion tells that what is the cache hit latency of the system if hit or miss comparison, which in this question is initially 1.3, if that becomes 0.6, what is the change? What would be the hit latency if both tag and data array access takes 3.5 nanosecond each and hit or miss comparison take only 1 nanosecond. So, there are 3 subdivisions. Let us take it one by one. So, we have to understand that there is 2 portions, there is tag array portion and data array portion. The tag array and data array are accessed parallelly, but access time may differ. Once the tag is accessed, after that only the hit or miss comparison time is applied. So, there is 2 wing, the left wing for tag array access followed by hit or miss comparison and the right wing for data array access which will take the data. Now, out of these 2 branches, whichever is the more dominant one, which is having more latency, that determines when data return can start. So, data return will start only if both the left side and the right side have completed the operation. Now, in first case, what is the cache hit latency? We know that the tag array access takes 3 nanosecond, that has been given in the question, and data array access takes 4.2 nanosecond. And this tag array section has hit or miss comparison logic, which has 1, which has 1.3 nanosecond. So, this is 1.3 and this takes 1 nanosecond. So, when you look at the left side, it will take 3 plus 1.3, that much is the time required to complete the tag array access and hit or miss comparison, and the right side will take you 4.2. So, left side is actually 4.3, 3 plus 1.3 is 4.3 and the right side is 4.2. So, the left side is dominant. So, it is 4.3 plus 1, this 1 is this data return time. So, the hit latency is 5.3 nanosecond. Now, the second question is, what is the cache hit latency if hit or miss comparison take only 0.6 nanosecond? So, this will become 0.6. Then the left side is 3 plus 0.6 and the right side there is no change, it is 4.2, that is data array access is 4.2. So, the dominant one is right side, that is 4.2 is the dominant one. So, 4.2 plus 1. So, your answer is 5.2 nanosecond. So, even though you reduce the left side from 1.3 nanosecond all the way up to 0.6 nanosecond, you are not going to get much rewards because the right side data array access is still the dominant fraction. Now, we move on to the third one. What would be the hit latency if both tag and data array access take 3.5 nanosecond? So, this has 3.5 nanosecond, this also will be 3.5 nanosecond, and the hit or miss comparison, this takes 1 nanosecond. So, the left side would be 3.5 plus 1, that is total of 4.5, and the right side is 3.5 only. So, the dominant fraction is left side, that is 4.5 plus 1, that is 5.5 nanosecond. So, even though the data array access got changed from 4.2 nanosecond all the way to 3.5, we are not getting rewards because the left side is now taking more amount of time. So, the next question is all about the relation between MPKI. MPKI stands for misses per kilo instruction. So, that is one of the important characteristic of a program, how many times I miss when I execute 1000 instruction, 1 kilo instructions. So, when I complete 1 kilo instruction, how many misses are encountered, that is called misses per kilo instruction, and you know that miss rate is number of misses divided by number of memory access. So, in this question, the MPKI of 2 programs A and B are 44 and 35 respectively. That means, when we run 1 kilo instructions of A, there are total of 44 misses. It can be misses in I cache as well as in D cache. Similarly, when we execute 1000 instructions of B, then there are 35 misses. So, MPKI of B is less than that of MPKI of A. Now, if 35% of A is data access instructions, what is the data access pattern of B if both A and B have the same cache hit rate? Now, A and B have different misses per kilo instruction, but as far as the hit in the cache is concerned, they are same. The number of access A make to cache and the number of time there is a hit in cache. So, number of miss divided by number of cache access is same in the case of A and B. That is why it is called cache hit rate is same. So, now in this case we have to find out. So, what we are telling is MPKI of A is 44, MPKI of B is 35, that is given in the question. What is mentioned here is hit rate of A is same as hit rate of B. That means miss rate of A and B is same. So, hit rate and miss rate will be same. Now, miss rate is defined as number of misses divided by number of memory access, or misses per instruction divided by memory access per instruction, because the instruction component is common. So, in numerator we bring in a parameter called misses by instruction, misses per instruction, number of misses per instruction divided by number of memory access per instruction. So, miss rate is defined as misses per instruction divided by memory access per instruction, MPI, misses per instruction divided by MAPI, memory access per instruction. Given that miss rate of A and B is same, so 44, that is the MPKI, misses per kilo instruction. So, if you wanted to get MPI, misses per instruction, then 44 is divided with 1000, because 44 is the number of misses for executing 1000 instruction. So, the number of misses for executing one instruction is 44 divided by 1000 divided by memory access per instruction. Here it has been mentioned that A has 35% of them are data access instruction. Data access means as per instruction pipeline, they are the load and the store instructions which are going to touch the data cache. So, 35% of the instructions are either load or store, they are basically data transfer instruction. So, we have to understand that for every instruction, surely there is one, we go to iCache, one iCache access is there, every instruction has to be brought. But out of 100 instructions, 35 of them will go to data cache. That means memory access per instruction is 1.35. This 1 is due to iCache and this 0.35 is due to Dcache. Or if you just imagine, out of all the instruction that is being fetched, none of them is load or store instruction, then I go to memory only for fetching the instruction. So, memory access per instruction is 1, just only once in the instruction fetch stage, and the mem stage won't be used. Let us assume that if all instructions are load or store instruction, then every instruction will go to iCache once to bring the instruction and to Dcache to bring the data or to access the data. So, in this case, since it is 35% is data access instructions, we have 1.35 as memory access per instruction. That is same as 35 divided by 1000, that is misses per instruction for B divided by memory access per instruction of B, which we do not know. So, if you solve the equation, memory access per instruction for B is 0.035 into 1.35 divided by 0.044. So, you get it as memory access per instruction for B is 1.073. We know that 1 is for iCache access. There exists always one instruction is being accessed for every cycle. So, once we have to go for every instruction, there is one memory access from the iCache. So, remaining is 0.073. So, 7.3% of instructions of B are data access instructions. Now, we move on to block replacement algorithms. Consider a 4-way associative cache that is operated in 2 modes. In mode 1, it uses pseudo LRU block replacement policy, and in mode 2, it uses last in first out block replacement policy. Assume that all the cache blocks are initially empty and filling up of empty blocks in a given cache set happens from way 0 to way 3. So, whenever the cache block is empty, you always fill way 0 first and then followed by way 1, way 2, way 3 like that. Once if all the blocks inside a cache set is full, that all the ways are full, then only replacement happens. So, replacement is using pseudo LRU if it is in mode 1 and LRU and then last in first out in the case of mode 2. Consider the following 14 block numbers that are mapped to a particular set given in the order of arrival. So, these are the block numbers, all part of the same set. So, they all these block numbers are mapping into the same set. So, they have to be kept in the 4 different ways. So, it is a 4-way associative cache, so in the 4 different way. So, if you look at the snapshot, let us say this is set number n and this set number n has 4 ways. At some point there may be A there, B, C, let us say F. Let us say this is the content. So, in set number n at a given snapshot, let there be block A, B, C and F residing. Now, when let us say there is a new request Q that is going to come, which one I am going to replace? Will I replace A or will I replace B, C or F? That is basically your block replacement question. So, find the number of cache misses that is happening excluding the compulsory miss in mode 1. Draw the pseudo LRU tree for set n after processing this request in mode 1. That is part 1 of the question. Find the number of cache misses including the compulsory miss in mode 2. Draw the content of set n way0 to way3 after processing this request in mode 2. So, this is basically the question. So, all the cache blocks are initially empty and filling up of the empty blocks will happen from way0 to way3. We have pseudo LRU block replacement policy, and these are all the block numbers that we are going to see. So, since it is a 4-way associative cache, we have a 3-node binary tree that tracks the pseudo LRU block. So, this is the root and these are the 2 children. After accessing a block, the arrows point to the least recently used direction. So, when you have the very first block A, then the cache block is empty or the cache set is empty. So, you keep A in the way 0. This is your way 0, 0th way, and this is way 3. So, to reach A, I am going to access A. So, from the root I want to go to the upper side. Since I am going to the upper side is the way how I access the recently used block A. So, the arrow should point down. So, this indicates the lower side of these 2 are the least recently used, and this indicate out of these 2, this is the least recently used. So, after accessing A, the LRU pseudo LRU tree looks like this, and it is a compulsory miss because A is accessed for the very first time. Now, let us say I am going to have the second request, that is B. When I am going to access B, since the cache set is empty, I am going to fill up way number 1, this is way number 0. So, when I go there from the root, still this side is the least recently used. That means this arrow point to the least recently used portion of the set. So, these 2 lines are the least recently used. When I come to this, then initially the arrow was down. In this case, the arrow is going up because when I access B, then out of these 2, the upper one, way 0, will be now the least recently used block. So, after accessing B, then the pseudo LRU tree looks like this, where the root is pointing down, the upper child is pointing to A, because after accessing B, A is the least recently used one. Now, going into C, so this is also a compulsory miss. So, compulsory miss, CMP stands for compulsory miss. When you go to C, C will be saved in way 2. So, to access way 2, I have to go to the lower side, this side. That means the arrow which was initially pointing down, now it has to be flipped up, because when you access C, it is the upper half of the tree that is the least recently used. So, always this arrow is pointing to the least recently used one. Since I am not touching A or B, whatever was the arrow position for the upper subtree, it will remain same. Here there were no arrows because the lower portion was not accessed. Now, for accessing C, you go to this particular block. Since I am going to that block, this arrow should point to the other one. So, these positions indicate which is the pseudo LRU position. So, to have a quick summary of what we have done till now, the root tells that the upper half is the least recently used. The upper child tells that again the upper half is the least recently used. So, if you look into this, at this point, this is the pseudo LRU block, because root tell upper, upper child also tell upper. So, A is the least recently used block as far as now is concerned. Let us continue further. The next block what we have, it is D. So, to bring D, that is again one more compulsory miss because we have space and D is accessed for the very first time. So, A, B, C, D. So, way 3 is being filled. Once you fill up 3, then this portion is untouched. So, it is same as what was there previously, and this was initially pointing to way 3, now it points to way 2. So, after accessing D, we have this as the position of the pseudo LRU tree. So, compulsory miss stands for whenever a block is demanded for the very first time, anyway it will not be available in the cache, and that is known as a compulsory miss. Now, continuing further, now we have A that is coming. When you go with A, you know that A is already present. So, that is known as a hit. So when you access A, till now the tree was like this, A is in way 0. So the root will be now pointing to lower side because current access was made to here, the upper side. So the arrow will flip there. The arrow which was there for C and D, there is no change in the arrow because we are not going to touch this portion. Since the access was to A, the arrow which was initially pointing to A, now it will be pointing to B. So it's a hit. So after accessing A, then the pseudo LRU tree wherein the root is having the LRU arrow towards down, upper child arrow is also to down and the lower child arrow is to up. Now it is B, B is also a hit. When you access B, the only change that happens is an arrow that was pointing to B, which indicates that it was least recently used. Since B is used now, this arrow will get flipped and this portion there is no change at all. This is also another hit. Now we have a new element E that is going to come. Here is the first replacement. So far there was no replacement, there are only compulsory misses. And now going to E, it is a miss. Now we have to find out which is the one that has to be replaced. So look into the status of it. Prior to bringing of the E, the pseudo LRU tree shows like this. If you travel through the arrows, you will see this is the pseudo LRU block because I travel through the arrows and I will reach this particular line. So out of A, B, C, D, at this particular juncture, C is the pseudo LRU. It is not the least recently used, it is a pseudo least recently used block. So the concept of pseudo LRU we have seen there during our lecture discussion. Continuing further, when you are going to have E that is been brought, E is brought for the very first time and E is to be kept in a place C. So C is been taken out because the arrow point to C. So whenever there is a new block that is coming, the pseudo LRU block will be replaced. Since I access C, this arrow should be flipped to down and my access was to lower side of the tree, then this will be the position of the arrows. This remained unchanged and this arrow will get flipped upwards. That is what is happening here. Since E is also brought for the very first time, that is a compulsory miss. Then we have F, you have to see that next element is F and we see that at this particular juncture after accessing the E, this is the way how which the tree looks like. So this is the point of arrows. So A is a pseudo LRU block. So naturally when we are going to bring F, since the cache is full, it is A that get replaced. So again it is a compulsory miss, this F is accessed for the very first time, A get replaced with F. So naturally this arrow get flipped to B and the root which was initially pointing upwards, now it is getting flipped down. So the root arrow will change and there is no change as far as this is concerned. Wherever this was there, it is unaffected. So when you bring F, the arrows in the root get changed and the arrow in the bottom child also will get changed. So whatever we have seen, so first 8 block request A, B, C, D, A, B, E, F that is been covered. Since I am moving into the very next slide, whatever we completed till now, this particular row will come up. So this is what we have completed till now. That is the position of the status at the rate of F. So this much is covered now. Now the next request is to A. We know that A is no longer present and A is a miss. And the pseudo LRU block at this point is D. So replacement of D happens. But A has already demanded in the past and now I am demanding for A once again, but it is not present. A is been evicted out in this process. So this is no longer a compulsory miss for A. This is called a conflict miss. So that is called CNF, conflict miss, where we know that D get replaced with A and since I am going to access the lower half, the LRU is pointing upwards. This side no change. This arrow get flipped. Previously it was pointing to the last block, now it get pointing into way 2. So this is the position at which this is there. Now we are going for B, but B is already there, so it will remain in a hit. It is not only counting it as a hit, but also the pseudo LRU arrow changes. So initially the arrow was pointing to B, now it get flipped upwards. Previously the arrow was pointing, the root arrow was pointing upwards, now that get also flipped because our access to B resulted in making this portion least recently used. So B is a hit. Now we have F, F is also a hit. So once you have F, it is a hit, this portion remain unaffected. The arrow which was initially pointing to F Now that got point to B. And then we have C. C is again a miss, but we have to understand that at this point the pseudo LRU tree looks like this. Whenever there is a miss for C, and C was accessed before, but now C is not present, so that is a conflict miss. It is not a compulsory miss. Compulsory miss is whenever we encounter a miss for the very first time as far as that block is concerned. So in this case, E will get replaced with C. This is also a conflict miss, and the arrows are changed accordingly because I am going to access the lower half. This will not get changed. The route, which was initially pointing down, now the route is pointing upwards. There is a change in the route. And since I access C, then this will pointing downwards. So always remember that the arrow is pointing to the least recently used portion. So we have completed up to C. Now there is only D. So whatever you see in the slide in the lowermost portion, this region, that is again redrawn in the next slide. So this is the position up to C. Now we have D that is coming in. We know that D is also not present there, but D was accessed before. So that time it was compulsory miss. This time D, it is a conflict miss, and D is going to evict B because the pseudo LRU tree points to B as the pseudo LRU block. So B get replaced with D, again one for conflict miss. So initial arrow that was pointing downward, now it points upward. Since the axis was to upper side of the set, the root arrow is pointing downwards and there is no change in the arrow. And the last one is A. A is already present there, so it's a hit. But after accessing A, the pseudo LRU tree looks like this. Now if you look at the statistics, there are out of 14 axes, 6 of them were compulsory misses. The very first axis of A, B, C, D, E and F. 3 of them are conflict miss, and then we got 5 hits. So now in this case, what we have done is, we have given with a set of blocks for a given set, and then we are processing them one by one, and every time an access is made, appropriate change happen in the pseudo LRU tree. Remember, the arrow get flipped. Whenever there is an access to the upper side, the arrow goes downwards. Whenever there is an access to downward side, the arrow got flipped to upper side. That is the way how it has been manipulated. So whenever there is a block replacement request that is coming, that means the cache is full, there is no place for the incoming one, we have to evict out somebody. That is a place where you find out the victim block. Victim block is found out by traveling through the arrows. So right from the root, travel through the arrows, that will be the pseudo LRU block. Now for the same question, we had a second mode wherein this last in first out was the block replacement policy. So we will now try to see. So last in first out can be easily implemented using a stack. So consider this as a stack. Let us say where 0 A is been brought, then B is been brought, so it is a miss, again compulsory miss, then C is been brought, and then D is been brought. So by this time now the particular set is full. It has blocks A, B, C and D sitting in way 0, way 1, way 2 and way 3. Now A is again coming, A is a hit, it is already present there. So A is a hit, that is been shown by the green color, no replacement needed. Then it is B, B is also present there, that is again a hit. Then it is E. This is going to create a miss because E is not present there, but it is a compulsory miss. But who will get evicted out? It is a last in first out policy. So D is the one who was entering into the stack last. So D get replaced with E. So A, B, C, E. That is a pattern in which you are going to get. And then we have F that is coming. Again F is not present, but this E will get evicted out, last in first out. So E will be replaced with F. Again compulsory miss, and then we have A, that is a hit. Then we have B, again it is a hit. Then we have F, again it is a hit. And then we have C, again it is a hit. And then we have D, but D is no longer present here. But D was initially brought at this point. So this is now a conflict miss, it is not a compulsory miss. So to bring in D, F is going out, last in first out. So D is going to come here, this blue color indicate conflict miss, and then the last one is A is a hit. So in this case, you can see that out of total 14 axes, there were 6 compulsory misses, 1 conflict miss and 7 hits. We move on to the next question. Consider a computer system based on 32-bit processor. So, this 32-bit processor is working on an 8 KB direct mapped on-chip I cache, 16 KB two-way set associative on-chip D cache. The off-chip unified cache is 128 KB, 4-way set associative. Block size for on-chip cache is 8 words and for off-chip cache is 16 words. So, we have been given the configuration of the I cache, L1 I cache and L1 D cache, and the L2 cache, the unified cache been given, and L1 cache has a block size of 8 words and L2 cache has a block size of 16 words. I cache is direct mapped, whereas D cache is two-way associative mapped. This is the 32-bit processor. So, the meaning is the word length is 4 byte or 32-bit. 4 fixed length instructions starting at main memory word address 22 in decimal are executed. So, we have 4 fixed length instruction with the word address 22, 23, 24 and 25. They are executed, and these 4 instructions refer to data at main memory word address 260, 261 and 275, all in decimal. Assuming caches are initially empty, indicate the non-empty blocks on all the caches after execution of the instruction. So, here in the given question, we have been given with a processor with 2 levels of cache, the L1 cache and the L2 cache, and the main memory is been given. 4 instructions are being executed. So, these instructions will be coming from main memory to the L2, the unified cache, and then to the L1 I cache. 22, 23, 24 and 25 are the word address in the main memory. They will come to some particular set in the L1 cache. Similarly, upon executing these 4 instructions, words 261 and 275 are accessed. Now, the question is, initially the cache is empty. Upon execution, there will be certain blocks that will be coming in, certain sets get filled up. We are supposed to find out the non-empty sets after execution of this. So, this question gives you a clear understanding of whether your understanding of mapping is correct. So, instruction words 22, 23, 24 and 25 and data words 260, 261 and 275. So, these are the ones that is being given 22, 23, 24 and 25 and data 260, 261, 275. So, location inside your main memory at L2 block size. So, from the main memory, so this is the main memory from where you are bringing to L2, and then we have the D cache as well as the I cache. So, these 4 words, it has to start from main memory, it has to reach L2 and then it has to come to I cache. Whereas, these 3 will come from main memory to L2 and then it goes to D cache. So, this main memory, when you transfer something from main memory to L2, it is a block of data that get transferred and it is equal to the block size of L2. So, L2 is divided with the block size of 16 words. So, if the word number 22 divided by 16, 23 by 16, 24 by 16, 25 by 16, these are all words which are part of block 1 in main memory. So, your main memory has block 0, block 1 like that. So, to find out word number n, it is part of which block, we have to divide it with the number of blocks in the word. So, when I divide with 16, I get it as B1. Similarly, location in main memory for L2 block size 260, 261 and 275. 260 and 261 will be part of B16, block 16, whereas 275 is part of block 17. So, when you find out the number of sets in L2, it is the cache size divided by block size into associativity. L2 is 128 bytes, so 2 power 17 divided by 16 words. So, that is 2 power 4 and each word is 4 byte. So, block size is 2 power 4 into 2 power 2 and it is a 4-way associative, that is associativity. So, I have 512 sets. So, main memory has block B0, B1, B2 divided based upon the block size of L2. It can go up to, let us say, thousands or lakhs of main memory blocks. But in my L2, I have only 512 sets. So, whatever be the block number B0 up to Bn, whatever be the block number in main memory, that has to map to up to 0 to 511 because I have only 512 sets in my L2 cache. So, my B1, so how will I know? It is a modulus operation. B1 and B1, when you perform the mod operation on 512, it get mapped to set 1 in L2. If the value was B1000, then we have to perform 1000 mod 512. If it is the 10,000th block, then 10,000 mod 512. So that's a process by which you find out, given the block number inside main memory, you wanted to find out where it gets mapped in cache. So B1 mod 512 is going to S1. Similarly, so when I bring B1, they all are part of the same block. So all these 4 words will come together and they get reside in set number 1, one of the block of set number 1, because L2 cache is 4-way associative. So one of the block of set number 1 is going to be accessed by this block. And B16 mod 512 we get set 16, and B17 mod 512 we get set 17. So one block of set number S1 will carry the instruction, one block of set number 16 will carry the words 260 and 261, and one block of set number 17 will carry block number 275. So these sets will be set 1, set 16 and set 17 will be non-empty in L2. Now we wanted to bring from L2 all the way to L1, but we have to know that the L1 block size is only 8 words. So we wanted to know whether this 22 by 8 and 23 by 8 will give you B2. They belong to block 2. So this is your main memory. So word number 22 and 23 belong to, this is block 0, then 1, 2. So 22 and 23, they were part of block 2 of main memory. It's a logically block 2 of main memory if you divide main memory as for L1 block size. You may wonder that you are transferring data from L2 to L1, but this is an abstraction of trying to understand how this mapping happens. Whereas word 23 and 24 is mapped to, so this is 22 and 23, this is 24 and 25. This is 24 and this is 25. So 24 and 25 will be mapped to block 3. Similarly, 260 and 261 will be mapped to block 32, because 260 by 8 and 261 also I am dividing with 8, you get 32, and 275 I divide with 8, you get 34. So number of sets in L1 I cache, cache size by block size into associativity. So L1 cache is 8 KB, so 8 KB 2 power 30, by block size is 8 words 2 power 3, into each word is 4 byte. So 2 power 3 into 2 power 2, that much is the number of bytes, because both the denominator and the numerator should be in same unit. So my numerator was in bytes, 2 power 13 bytes, so denominator also should be in bytes, it should not be in words. That gives you 2 power 8 sets. So my L1 cache has 256 sets. So whatever be the block number, at the end when it been mapping, it should map get to 0 all the way up to 255. So B2, when I perform a mod operation, B2 get mapped to set 2 of the L1 I cache, and B3 get mapped to set 3 of L1 I cache. So the word number 22 and 23 will reside in set 2 of L1 I cache, and word number 24 and 25 will reside inside set 3 of L1 I cache. So set S2 and S3 of L1 I cache will be non-empty. Similarly, we find out the number of sets in L1 D cache, cache size by block size into associativity. Here cache size is 16 KB, so it's 2 power 14. Block size is 8 words, so 8 words into number of bytes in a word, it's 4 byte. And it's two-way associative. So here also you have 256 sets. So block 32, which we have already identified it as block 32. Block 32 mod 256, it get maps to set 32. Block 34 mod 256, it get maps to set 34. You may find that this block number is same as a set number, because all the block numbers are lower than 36. If the block number value, let's say Bx, where x is larger than 256, let's say block 300. So it should be 300 mod 256, that is the number that you get. So one block, so it's a two-way associative cache. So in set number 32 and set number 34, out of the 2 block, one block will be non-empty. L1 D cache will be non-empty in that scenario as well. So this particular question, what we have done is, we have considered the specifications of I and D cache, and we are mentioning what are the words that processor is trying to access, and based upon the mapping from main memory all the way to cache, we are able to find out which are the sets that are getting filled up, which are the non-empty sets. With this we come to the end of this tutorial. With this tutorial you might have got a fair understanding of the mapping and the replacement techniques that is being used in cache. In the Hennessy and Patterson computer architecture textbook, there are plenty of problems that are given at the end of the memory chapter. So solving these exercises will give you more grip on understanding this topic. I hope the tutorial session was useful. Kindly try to solve out as much as problems as possible and get back to us if at all you have any query. Thank you.